starting chapter 15, which is entitled Equilibrium or Chemical Equilibrium. In chapter 14, we learned all about chemical kinetics, which is a study or it focuses on rates of reactions and how fast reactions proceed at certain moments in time. But what that doesn't say is anything about how far reactions are going, right? So not all reactions go to completion, which you already know. If you look at a first order reaction, you know that the speed of the reaction decreases as the reaction proceeds, and that you never really reach the end. And so chemical equilibrium and thermodynamics will tell us a little bit more about how far a reaction goes. The example that the book is using is hemoglobin. Hemoglobin is a fairly complex structure that's responsible for oxygen transport, and there is an equilibrium, or there is a factor that makes the oxygen transport from the lungs to the muscle. And we'll look at that in a little bit more detail, but first I want to review reactions and tell you exactly what I mean by chemical equilibrium and chemical reactions that don't complete. This reaction is quite obviously a reaction that goes to completion and there is no going back, right? So nails rusting may be a very slow reaction, as you know, so the chemical rate of the reaction of iron and oxygen going to iron 3 oxide that's shown here is a very slow reaction, so it's kinetically not favorable, but thermodynamically it is. And so once you have iron oxide, there really is no going back, so that's not a reversible reaction. And most of the reactions you've seen have this reaction arrow that is one-sided. But that's not always true. We have reactions that have a forward reaction and a reverse reaction. And the concentrations of products and reactants, there's some always present at any time of this reaction. So they don't go to completion at all. An example is carbonated water. Carbonated water is basically water that has been pressurized with carbon dioxide. It can be pure water or it can be a already existing solution. What happens is if you take water and you bubble carbon dioxide into it, or you pressurize it with carbon dioxide, the carbon dioxide will react with water to form carbonic acid. And so initially when you pressurize the water, you have no carbonic acid, so the forward reaction, the rate of carbon dioxide and water, proceeds at some rate. And so you have this forward reaction as I've shown here. But the minute the carbonic acid forms, it actually decomposes. It reacts back and forms water and carbon dioxide. And so that's shown. I've simply written it in the reverse reaction. So that is a reversible reaction, and that can be indicated with this double arrow here. So this means it's a reversible reaction. So you have some sort of forward rate and some backwards rate. And if you seal this off, like in this can, you can actually prevent the carbon dioxide from escaping, and you will come to some sort of chemical equilibrium. You will have a moment where the rate of the formation is equal to the rate of the decomposition, and at that point you can measure the concentrations of each of these reactants and products, and they will not change. And when that occurs, we say the reaction is at equilibrium, and then we use this double arrow here that's slightly different than the one that indicates it's a reversible reaction. Now that's still a reversible reaction, except it means it's at equilibrium. So most of the time you'll see this reaction arrow and not this one. So we can of course disturb this arrow, or we can manipulate this equilibrium by simply opening up the can. And this is referred to as Le Chatelier's principle. We can shift this equilibrium, or the position of the equilibrium, or the rate. We can make the forward rate go, or the reverse rate. We can, depending on how we manipulate this. And by simply opening up the can, what you're allowing is the carbon dioxide to escape. So since it's a gas, you know this, it's bubbles, and if you leave it open, it's going to go completely flat over a few hours, or at least by morning. If you heat it up, it's going to speed that process up even more. But what's happening is you are allowing carbon dioxide to escape. You are taking out a reactant, and then the forward rate or the reverse rate, the carbonic acid, will then further decompose to reach that equilibrium. So the driving force is that to get back to an equilibrium. And so if you seal that halfway through, you do get to an equilibrium where the concentrations are now different. Okay, so let's review these different kinds of arrows. So this is the one we're most familiar with. Those are reactions that are not reversible. They go to completion and then they're done. Those are usually thermodynamically favorable. They can be reversed, but not naturally or not on its own. You have to stick some sort of energy in. And then we have reversible reaction. And so this arrow and that arrow differ only. These are both reversible reactions, except the one here means at equilibrium. You've seen this arrow already. It's the resonance arrow. It goes back to when we were drawing Lewis structures. Now the example shown here is for an organic molecule, but if you remember, you can draw sulfur dioxide, and you can either draw it with a double bond to the right, or there's a resonance structure where you can shift these electrons this way, where now you have a double bond on the left and a single bond on the right. And so this is just the position of the electrons, or the way the electrons are distributed. Those are called resonance structures, and we use this resonance arrow. And then there's one that you've not seen before. It's a broken arrow, which means there is no reaction. And so sometimes it can be important to see what the potential here is. Like copper can oxidize to form copper sulfide and magnesium, except magnesium has a higher reaction potential, and therefore the reverse reaction only occurs and not the forward reaction. So we would write NR, there's no reaction, but that's what this means. All right, so let's take a look at an example. This is a very nice example here. If you, and it has a color feedback, and this is why it's ideal, because we can kind of see how the equilibrium shifts, or what species, reactants, or products are dominant. And so here, in this case, the reactant in this reaction is COCl4, and it's blue. And the major product in the reactions is pink here, the COH2O6. It's an hexa-aqua-cobalt-2 complex. It's called a complex ion because it is charged. This is also a complex ion. So if you take cobalt chloride, cobalt-2 chloride, for example, and you dissolve it in water, what happens is what happens is you get cobalt ions and chloride ions. So that's a given. It's soluble, it breaks into its ions. And then if there's water, 6 water molecules surround this cobalt and form this pink hexa-aqua-cobalt complex. And then the chlorides are also in solution. But once you form that, a little bit of this chloride will react with the cobalt and form COCl4. But if you have a lot of water present, you're not going to see this blue species. There's a little bit left. You'll have a pink type of feedback. Now, if you take anhydrous cobalt chloride, meaning there is no water, it's a blue powder, and you dissolve that in ethanol, you actually get a blue solution. All right. So if you take cobalt chloride, you don't have any water present, it's going to make a blue solution. We're going to do this in the lab. We're going to prepare a solution in ethanol of cobalt-2 chloride that is right on the border between having predominantly pink and predominantly blue. And so the way you do that is you dissolve your cobalt-2 chloride in ethanol, and then you slowly add drop-wise water to it. And so that what will happen is this species here will slowly react with water to form this pink complex on the right, and when it turns from blue to pink, you stop, and that's when we can shift the equilibrium. We can either then meaning we can either make the forward reaction go or the reverse reaction go. And then if it stays blue, that means the reverse reaction is predominant. If it turns pink, then we caused a forward reaction to proceed. And so you can manipulate this equilibrium with this Le Chatelier's principle by either adding reactants or products or taking reactants and products out. That will shift it. It'll put a stress on the system, and it's going to try to get back to an equilibrium. So any of these products here, so if you add more water to that, you will increase the reactant and it will push to the right, meaning it shifts to the right, and you're going to produce actually more pink. You can also take water out and it will shift to the left and it will make it more blue, or you can add a chloride, a source of chloride for example, and it will shift to the left. So I also have this heat here, right? So heat here is added to the product side, which means this is an exothermic reaction. If you go back to chapter 9 or 10, depending on what book you used on thermochemistry, we said that exothermic reactions that have a negative delta H have heat on the product side, right? It releases heat, so heat is part of the product. If it's an exothermic it's an endothermic reaction, heat is part of the reactants, which means you have to stick heat in order for the reaction to proceed. Well, because heat can be a part of the product or the reactant, depending on what type of reaction that is, you can manipulate equilibrium like that as well. So this is exothermic. So if you stick heat in, meaning you are heating up, you're going to shift this to the left and it will turn more blue. And if you take heat out, like you stick it in ice, it's going to shift it to the right and you're going to produce more of a pinkish color. So again, this is referred to as Le Chatelier's principle. So take a look at this reaction. We're going to shift the equilibrium. As I said already, adding a product or a reactant can favor one or the other direction of this equilibrium. So if you add water, what you're doing is you're adding a reactant. Water is a reactant, therefore it will shift to the right and make the solution more pink. You are going to see an increase in the pink species and a decrease in the blue species. That doesn't mean the blue species is gone completely. We still have some. We just can't see it in the concentration of the hexa-aqua species is higher. If we add either solid sodium chloride or a solution of hydrochloric acid or a solution of sodium chloride, that's a source of chloride, and chloride is part of the product, right? So if you remember, if you have hydrochloric acid that's aqueous, it breaks completely into chloride and hydronium ions or H+ ions, and so does sodium chloride. It's water soluble. AQ means we have sodium and chloride ions in solution. So if we add that to a test tube that has the reaction above in it, what you're doing is you're increasing the product and therefore will observe a shift to the left. So here there's a source of product which affects this equilibrium as a product, therefore shifting it to the left, making the reverse reaction rate increase until again we come to an equilibrium. And so the sodium ions and the hydronium ions, they don't do anything. They're kind of like spectator ions. So this will cause a shift to the left, and you should observe an increase in the blue color or a shift from pink to blue. Adding silver nitrate is a little bit more involved because neither silver nor nitrate are present as a reactant or a product. But you also have to remember the solubility rules, that silver actually will react with chloride to produce a precipitate. So silver chloride is not soluble. And so if you have silver ions and chloride ions, they're going to precipitate out, meaning they're no longer in solution, or the chloride here is no longer in solution. So you will see a decrease in chloride, which will make the reaction shift to the right towards the pink end, and therefore decreasing the concentration of the COCl4 and the water, but increasing the concentration of the COH2O6. Okay, and then technically also heat it up a little bit. And then finally, if we cool and heat this, it should also have an effect, because as I said, for this exothermic reaction where heat is a product, if you heat this reaction, meaning you stick more heat in, that's just like putting more chloride in. It will shift this to the left. So heating this reaction actually promotes the reverse reaction here, and it should turn more blue. Whereas when you stick this in ice, that's as if you're taking out one of the products, which is heat. You're cooling it down, you're taking out heat. It's going to shift it to the right. So that's what's shown here. If you take that blue test tube, depending on what the concentrations are initially, you can make this, definitely will shift to the right, and you'll get a visual cue from that. Okay, so that's just to introduce Le Chatelier's principle and chemical equilibrium, and it's a good point to spot, to stop, to spot, to stop, to stop. This is a good point to stop.